Welcome. This video is about our work on myoelectric model-based control of a bilateral robotic ankle exoskeleton during even ground locomotion, presented in BioRob. Finding new solutions for the intuitive control of exoskeleton is a key challenge today. Although research has led to sophisticated robots, this device cannot be controlled directly by the subject. Current exoskeletons are controlled externally using predefined joint trajectory or torque profile, which are pre-designed beforehand, and in some cases they may be prescribed as a function of the gait cycle, but the shape and timing of this profile is fixed and not determined by the central nervous system. In this context, the exoskeleton is driving the subject, not the other way around. And that's the problem we want to solve, because this impairs translation to assistive device setting in general. The goal is to enable subjects to control exoskeleton across a wide range of working conditions. For this, first, we need to understand how movement emerges from the interaction between the central nervous system and the musculoskeletal system, and how exoskeleton can become part of this neuromechanical interaction. If we can do this, then we can really go from exoskeleton to exomuscle, artificial actuator controlled by the central nervous system, acting directly on the musculoskeletal system. One of the solutions to this goal is the use of real-time neuromusculoskeletal modeling, which enables creating virtual twins of an individual person. This model contains numerical representation of the musculoskeletal system, but also incorporates formulation to infer how the nervous system controls the neuromusculoskeletal system. The model can be personalized to a patient to reflect their residual muscular capacity by being informed directly by experimentally recorded EMG and joint angle. This allows computing muscle and joint torque that can be then used to enable voluntary control of an exoskeleton. We developed our human-machine interface for exoskeleton based on neuromechanic modeling. From the user, we record EMG and joint angle. We filter and normalize EMG using maximal muscle activation recorded before the trial. Filtered joint angles are sent to a musculoskeletal geometry model where muscle tendon length and moment arm are computed using a B-spline algorithm. Muscle length and muscle activation are sent to the musculoskeletal dynamic stage, which computes muscle tendon force using a Hill-type muscle model. These values are then used to compute the biological joint torque via moment arm estimates. Torque is then multiplied by a support ratio that is given to the torque controller of the exoskeleton, which will give mechanical assistance to the user. Finally, to obtain precise joint torque estimation and be able to estimate residual muscle capacity of the patient, personalization of the model to the user is crucial. For this, we first going to scale the musculoskeletal model, and then we are going to adjust the parameter of the muscle model using an optimization that is going to reduce the error between experimental joint torque and the estimated joint torque. To test the neuromechanical model-based controller, we realized experiment on 4 subjects. The working conditions were a mix of 2 different speeds and 3 different inclinations. We compared the assistance from our controller and a non-assistance condition using transparent mode. The recording was done in one long trial so that we could also test the change in working condition. In this video, we can see a subject working at 1.8 km per hour. In purple, we can see the biological ankle joint torque, in blue the torque assistance, in green the soleus muscle EMG, and in red the tibialis anterior muscle EMG. We can see a net reduction in biological torque and EMG amplitude. We're then going to present the change in speed and how our assistance is modulated to adapt to the new working condition, without having to switch between assistance pattern or change any parameter in our controller. Reduction in biological torque in dark blue and purple was achieved in all tested conditions as well as during transition between conditions. Importantly, when the exoskeleton torque in light blue and purple is added on top of the biological ankle torque, we can see that the total amount of torque needed to locomote is similar. Only the biological torque during assistance from our human-machine interface is reduced, with the assistance taking up over a percentage of the torque generation to locomote. The second result is the effect of our assistance in blue on the EMG. As we can see, when compared to minimal impedance in purple, we can achieve a reduction for all tested conditions, and more importantly, we could achieve reduction during the transition between conditions. This is central to achieve a controller that can assist during daily task activity. This was done without having to change any parameter in our model or controller. Since our human-machine interface knows the user intent, it can automatically adapt to new and unknown tasks. Most of the reduction was achieved for the soleus, which is strongest muscle in the ankle and produces most of the propulsion during walking. Future work will be done by testing the working condition on patient and develop an algorithm to continuously adapt muscle parameters to adapt to fatigue and reduce the time between the calibration of the model and subject testing. The take-home message are that neuromechanical model-based control can be used to offer continuous and voluntary assistance over a broad range of working conditions, as well as during the transition, while offering biomechanical benefits. This study was supported by the ERC starting grant Interact.